Hey folks, ever wondered just how deep the universe goes? Like, what's the smallest thing that exists? Well, today we're diving into the Planck scale, where lengths are so small they make an atom look gargantuan. We're talking 10 to the minus 35th meters. Yeah, minus 35th. How does reality behave at scales that tiny? Could spacetime stop being smooth and continuous and instead look kind of like a pixelated screen? Let's take a closer look at this incredibly strange, almost sci-fi realm. Alright, to start, the Planck scale represents boundaries where our current physics, classical mechanics, general relativity, and even quantum mechanics stops working so well. Named after Max Planck, one of quantum theory's pioneers, the Planck length isn't just small. It's more like unimaginably, absurdly small. The equivalent of slicing a millimeter into lengths smaller than the difference between galaxies. But here's where it gets really weird. Anything measured smaller than this might lose its meaning. Not because we lack better instruments, but because space-time itself might not exist in the same way. Now, let's lay out something critical. Space-time, as you may know, is often visualized as a continuous fabric. Thanks, Einstein. But on this minuscule scale, space-time could possess a discrete, grid-like structure. Imagine zooming in, and instead of smooth curves, you find tiny, indivisible blocks, quantum pixels, if you will. Calling them pixels isn't exactly correct, but it's kind of the right analogy in terms of how discrete everything might become. What causes this? Well, there's where quantum gravity theories come into play. You see, general relativity works great at giant scales: planets, stars, black holes. Quantum mechanics work swimmingly for the micro world, atoms, electrons, and all that. But put them together, like inside a black hole or at the instant of the Big Bang, and they just stop playing nice. Everything breaks. Terribly. Physicists believe this discord is a key piece of why space-time might get quantized. Enter theories like loop quantum gravity or string theory to try and explain it all. Now, let's focus on loop quantum gravity for a second. Some researchers think space-time might be made up of tiny loops of energy, sort of like knitting patterns, but on a scale we can't comprehend. These loops could combine into areas, surfaces, and even volumes, but each being fundamentally indivisible. These tiny loops might even resolve the idea of a singularity, a place where the density becomes infinite, like at the center of a black hole. Instead of an infinitely small point, these loops might impose an ultimate size limit on how small anything can be. All right, but what about string theory? Strings paint an entirely different picture. Instead of space-time being cut into blocks, it suggests our universe essentially emerges from the vibrations of one-dimensional strings. These strings vibrate differently to form everything, from particles to gravity itself. While the theory's entirely mathematical for now and not experimentally verified, it's fascinating. Even more so because it requires extra dimensions beyond the 4 dimensions we understand: 3, space, and 1, time. If strings are real, these dimensions are tightly compacted, coiled smaller than even the Planck length. But, okay, let's talk about the speculative punch. Are these ideas just neat or actually useful? Well, it's hard to say because, at the Planck scale, we can't measure directly. We'd need energies absurdly beyond what's feasible, even for futuristic particle colliders. However, scientists rely on indirect evidence. For example, black hole physics tantalizingly hints space-time might not be smooth. Hawking radiation, or particles leaking from black holes, suggests quantum-scale weirdness intertwined with gravity. Let's go deeper, though. The Planck scale has monumental philosophical implications. Does space-time pixelation mean reality has a fundamental resolution, like a video game? And if so, what lies beyond it? If space-time's pixels exist, is there an underlying architecture? What would it mean for causality? For the notion that event A leads to event B? What's truly behind reality itself? Quantum gravity debates, like ADS-CFT correspondence, suggests spacetime could be an emergent property. Geometrical space we see could simply pop out from more abstract quantum information. Some researchers push even further to speculate whether the universe itself acts like a constantly computing system, processing reality in fine bits of spacetime. But here's the head-scratcher. If spacetime is digital, who or what is running that program? Mind-blowing, right? Anyway, we've just scratched the surface, but you're probably sensing already how mind-bendingly complex the Planck scale is. And that's why this mysterious boundary is at the frontier of physics. There's so much to explore. Quick note before you go. It's a new channel, and your comments and feedback help shape what we'll dive into next. As always, stay cruised, stay hyper-focused, and remember, at this scale, reality itself might just break down into pixels,